So, with this brief video tutorial, we are going to use the Anaklasis package in order to fit the ORSO example data. Here you see the page on GitHub of the project where you can find information about the general features of Anaklasis and also guidelines about how to install the package on Linux, Mac OS, and Windows. On this particular MacBook, I have already installed the package, so we can go straight ahead and first inspect the example data by opening them with a text editor. So you can see here in the comments that we are dealing with a silicon oxide polymer D2O system measured on a neutron reflectometer. And also we see that we have 4 columns of data. So wave vector transfer, reflectivity, error in reflectivity, and delta Q information. In order to fit this reflectivity curve with Anaklasis, we need to write a script. And in order to do this easier and faster, we have some templates here in the script templates folder. We pick the one for fitting single reflectivity curves. We paste it in the directory where we have our data, and we open the script template with the editor that we prefer. So a script analysis essentially consists of a section where we put some information concerning our data. We then define our model and model parameters. We insert some information about the instrument, and then we just call the fit function in order to fit our data. So first, we begin by giving a name to our project. So here we will name it ORSO example. Then we have to define the name of the data file that contains the data. In our case is ORSO example.ort, as we see here. Our units are in angstrom, so this is correct. And then what we have to do is that we have to define the model at the interface. So the model is defined here in a list structure where we have the fronting, backing medium, and also the layer in between. Since we have 2 layers in our case between the fronting and the backing medium, let me paste another line here. And let's start with the fronting medium. Our fronting medium is silicon. Let's put here a description, silicon. Then we have to define the real part of the SLD, which for silicon is 2.07 10 to the minus 6. We will leave all imaginary SLDs equal to 0 because for the materials involved in this experiment, they are all very small. For the roughness between silicon and the first layer, we don't know the value, so we are going to use a parameter here. So let's say P0. We assume no solvent penetration here, and we are done with the fronting medium. Let's do the same for the backing medium. Our backing medium is D2O. We put D2O in the description. The real part of the SLD is 6.35 10 to the minus 6. And also it's a liquid, so solvent is equal to 1. Now for the 2 layers in between, the first layer it's a silicon oxide layer, so silicon oxide, the description, SLD 3.45 10 to the minus 6, that is correct. The thickness of the layer we don't know, so a parameter P1, we have already used P0. Roughness, also we don't know the roughness between silicon oxide and the polymer, so here we will put P2, another parameter, 0 solvent penetration, and we are done with the silicon oxide layer. Next layer is the polymer layer, so we give a description polymer. SLD, we don't know the SLD of the layer, so we are going to use a parameter here, it's P3. 0 imaginary, SLD thickness, we also don't know, so P4, another parameter. Roughness between polymer and D2O, we don't know, so another parameter here, P5, and we assume zero solvent penetration since we left the real part of the SLD free. And also our backing medium D2O has already the correct values. Now, since we are not dealing with a mixed area model, these two lines should stay as they are. And then we go to define the bounds and the description of the parameters we used here in our model. Since we have in total in the model 6 parameters, let me copy paste some lines here in the list in order to have 6 lines. Great. So P0 is the roughness of the silicon layer. Let's put here bounds from 0 to 10 angstrom, and let's put here the name of this parameter as silicon oxide roughness. Now, P1, the next parameter is the thickness of the silicon oxide layer. So P1, let's say that it is from 0 to 50. Let's leave the bound quite open. And let's name this parameter as CO2 thickness. Next parameter, P2, is the roughness between silicon oxide and the polymer. So P2, let's put bounds from 0 to 20, again quite wide. And let's name this as CO2 polymer roughness. Now, parameter number 3. Parameter number 3 is the SLD of the polymer. Let's say that we go from 0, 10 to the minus 6 up to 3.0, 10 to the minus 6. And let's name this parameter as polymer SLD. Parameter number 4. Parameter number 4, it's the thickness of the polymer layer. Let's put this parameter to go from 0 to 300 angstroms. And let's name this as polymer thickness. And final parameter, parameter number 5, P5, is the roughness between the polymer and D2O. Let's leave this parameter also to vary between 0 and 50. And let's name this as polymer roughness. So we have defined the description and the bounds of each of the parameters that we have used here in our model. Next, we have the multi-parameters that we don't use in our case because they are used when we do global optimization of multiple solvent contrasts. Constraints. So we can add some constraints here during our fit. For example, we want always the roughness of the layers to be smaller than the thickness of the layers. So for example, we want P2 to be smaller than P1 and P5 to be smaller than P4. So what we can do very simply is to include these expressions here in the constraints list. So we want P2 to be smaller than P1, and also another expression, we want P5 to be smaller than P4. And that's it. During the refinement, these inequality expressions will be respected. Now about the resolution, since we have information, delta Q information in our input file, we can perform point-wise resolution calculations. So we set this equal to -1. In the case where we didn't have the fourth column, we should have placed here the delta Q over Q of our instrument. Background, we leave the background also a bit free between 0 and 10 to the -6, which is a typical value for a neutron reflectometer. And also the scale a bit free between 0.8 and 1.2 in case the scaling of our data was not perfect during the measurement. Finally, concerning the fit, we will use the default chi-squared with errors figure of merit, fit weight equal to 1 because we just have one reflectivity curve and we cannot do weighting between curves. And also the method that we are going to use here is simple, so a differential evolution minimization with an estimation of the Hessian matrix for calculating the parameter uncertainty. Then the last thing here in our code, we call the ref.fit function that performs the optimization, and we pass the results here in a dictionary called res. So we save here the script and we open a terminal window in the directory where we have our data and the fit script. So let's see here, good. So we can run our script, Python 3 fit single curve in order to run the optimization. First, the differential evolution minimization will take place. It's done, and now the estimation of the Hessian matrix, and we wait for a pop-up window with the results. Here it is. So you see here the fit of our data. We reached a quite good chi-square 2.7. Here you see the R q to the 4 versus q of the data and the fit, and also here the R versus q of the fit and the fitted curve, and also here a window giving us the SLD profile and also the solvent profile for our system. We get a pretty decent fit here at the end. You can see here in the terminal window, we have information about the values of the parameters and also about the uncertainty of its parameter, information about the chi-square, about the background that was fitted and the scale that was fitted. And except from the output here in the window, we have also a folder where we have exported all results in the form of ASCII files and also in the form of PDF plot. So for example, here we can open the reflectivity .pdf where you can see here the fitted curve and also the residuals from the fit. Now, a thing that we can do if we want to go a bit further is that we can use a Markov chain Monte Carlo sampling of our system in order, except from a parameter estimation, parameter uncertainty estimation, also to get a correlation plot between our parameters to see if there are any covariances between our parameters, the ones that we used in model building. This can be done very simply here by changing this method here from simple to MCMC. We save the script and we just rerun it. Now, this calculation will take a bit more than the previous calculation that we did, where we estimated the uncertainty just by estimating the Hessian matrix. For this particular system, it will take around 5 minutes in order to obtain the results. But at the end, except from the fit, we will also get this correlation between the parameters. So after about 4.5 minutes, we get here the fit, pretty much the same thing as we had previously with our initial run. Here you see the SLD profile, the silicon oxide, the polymer layer, and then T2O. And here nicely our reflectivity curve fitted. But with MCMC, as we said, we have also exported a correlation map. We can go here in the directory where in our work directory and open what we call the corner plot, where you can see here a plot, correlation plot between the parameters. where you see that we have no serious correlation between the parameters except a moderate correlation between the thickness of the silicon oxide layer and the thickness of the polymer layer, where you see here in the plot, in the surface plot, the structure a bit elongated. So that's pretty much it. The fit of the ORSO data with Anaklasis, and happy fits to everyone.